Hello, this is Team 3, and we are going to present the proposal of our course project of CS572. For the paper, we choose to implement the paper named Cascade Flight Control of Cloud Router based on deep reinforcement learning. And the reason for choosing this paper is that it is belong to our interest topic, which are robotics and control. For the introduction, the paper proposed deep reinforcement learning-based Cascade Flight Controller for cloud routers. They are motivated by the fact that the classic deep reinforcement learning cloud router has only one single policy network, as can be seen from the left figures, and that takes the state and desired values of the state as input and directly output the control variables and also regard the dynamics as black box. And this requires a substantial amount of training time and complicated hyperparameter tuning. And to overcome these issues, the paper proposed a cascade slide controller where the cloud router dynamics is considered and decomposed into the position and the attitude subsystem that connect in the cascade form and utilize multiple policy networks to control each subsystem instead of single policy networks, as can be seen in the right.
Lots of computation and hyperparameter tuning in DRL leads to long training time. The graph shows the time needed to train a UAV with DRL method. In paper 1, DRL is applied to track desired angular velocity. In 2, the multiplicative reward is used to RL for control tracking desired angular velocity to prevent underestimating reward terms. In 3, the agent runs low-level dynamics of the UAV and use the run dynamics to hover. The selected paper tried to improve the training time and achieve tracking performance with short training time.
And so by doing that, there are three main methods in this paper. The first one is the linearization of the corridor dynamics. The second one is the cascade controller, and the third one is the training process. For the linearization of the corridor dynamics, as can be seen in the full dynamics form on the left, the rotation matrix is the function of low and pitch and yaw angles, and thus the translation and rotation are coupled with each other. And to decouple this, the dynamics need to be linearized, and one way is to make the small angle assumption, where row and pitch angles are assumed to be close or equal to zeros, and thus the linearized and decoupled form of the dynamics, as in the right equation, can be obtained. For the cascade controller, after the dynamic is linearized, each part are now decoupled from each other, and 6 subsystems can be obtained, which are X, Y, Z for the position subsystem, row, pitch, and yaw for the attitude subsystem. And thus, the controller can be designed individually for each subsystem, the cascade controller form. And the controller consists of 6 policy networks in total. And in fact, each controller contains a neural network that has 2 hidden layers with 32 nodes, followed by rectified linear unit activation function. And in addition, it can be seen from the below figures that the output of the policy networks of the position subsystem will be the input to the policy networks of the attitude controller, and thus they are connected in the cascade form. For the training process, since 6 subsystems are obtained, each network can be trained individually and in the sequence manner. So first, the yaw controller is trained, and followed by pitch and low controllers, and then the C controllers will be trained after this, and X and Y controller in the C sequence. And to train the networks, 3 model-free deep reinforcement learning algorithms are employed, which are PPO, DDPG, and TD3 to train the networks. And using this approach, the deep reinforcement learning cascade controller, the paper shows that the training time are shortened, which are 8 minutes for PPO and 17 minutes for DDPG and TD3. And also the tracking performance is superior than the conventional control method like PID control. And for the replication plan, since the paper provides an open source code for training, so we will replicate the results of the paper and also combine the training source code with the piloted drone simulators and OpenAI gyms, which are gym piloted drone, and to visualize the flight of the cloud router. And since the open source contains only TD3 algorithms, we will apply the other two, which are PPO and DDPG. Maybe we employ from the stable baseline 3 library.
our plan is to remove the small angle assumption in the paper we choose. In the paper, position controller needs small angle assumption as X and Y are directly connected to roll and pitch. Attitude controller also needs the assumption that roll and pitch and yaw angle have a direct relation with each component of torque. To elevate the assumption, we add two additional blocks to the original controller, which are the transformation block and the attitude controller block. This is the overall architecture of the proposed controller. From position controller, we generate acceleration commands. The transformation block receives the acceleration command and desired yaw angle and outputs the thrust and angular velocity command. Then roll, pitch, and yaw controller outputs torque commands to track angular velocity commands. After that, torque and thrust commands are converted to the commands for each motor. X controller receives EX and EU, which are position and velocity errors in the x-axis, and U D dot, which is the desired acceleration in the x-axis. Its output is an acceleration command. The reward is the difference between the next and current norm of position and velocity. Y and Z controller has the same structure with the X controller. Transformation, acceleration, and yaw to the transformation block transform the acceleration and yaw to the desired thrust and rotation. FC is mass time norm of the acceleration plus gravitational acceleration. The direction of the acceleration is the desired body z-axis, so we can get the desired roll and pitch angle. With the desired yaw angle, we can generate desired attitude RC, which is rotation matrix. Attitude error for the attitude controller, the error is defined as ER is 1/2 times RD transpose R minus RD, R transpose RD and V operator. Omega and the omega angular velocity command omega C is minus K1 times ER. And we assume the desired angular velocity is small. For the roll controller, let the components of the current angular velocity omega and angular velocity command omega C as follows. The error is defined as EP is P minus PC, and the output is torque applied on the body axis. The reward is defined as the difference between the current and next norm of the error. The pitch and yaw controller has the same structure of the roll controller. Thank you for listening.